right, we're back. This is still, we're in section 2.1 and 2.2. We're looking at shear strain. And I think this is example number 2. So we have a 16 by 22 by 25 millimeter. So here it is zoomed in, 16, 22, 25 goes back in the page. Rubber blocks are used in a W shear mount to isolate the vibration of a machine from its supports. An applied load of 690 newtons causes the upper frame to be deflected downward by 7 millimeters. Determine the average shear strain and the shear stress in the rubber block. Okay, shear strain and shear stress in the rubber block. So I went ahead on this one and included the free body diagrams just because they're much neater than what I would have drawn. So here's a shear block. Here's the system. I'm pushing down. Okay, as I push down, it's going to cause this deformation, and we can see we've gone from a perpendicular cross section to that skewed look, kind of like if I were slicing bread and the bread wants to kind of go down. Okay, we have that it's 16 millimeters in this direction. It's 22 millimeters tall and 25 millimeters back into the page. So if I'm looking straight on, then I can see that we are 16 millimeters and 22 millimeters, and then it would be 25 millimeters back into the page. Shear strain is gamma. Gamma is shear strain. It's that deformation. And the story problem told us that we had we went down a displacement of 7 millimeters. The whole thing is 22 millimeters. So if we assume small strains, then I know that gamma equals delta over L. This is my delta. That's how much we had in displacement. L is my original length. So see that triangle right there? There's my little triangle. You can also see that this is going to be a positive because this interior angle became smaller than 90 degrees, pi over 2. So my shear strain equals 7 millimeters divided by 16 millimeters. Those units go away. I'm left with 7 over 16. So I find that my gamma is 20. Oops, not 20. I don't know where my brain is tonight. Is 0.4124 radians. If you wanted, you could also go back and say tan gamma equals 7 over 16. And then you could take the inverse tan, and we could find that gamma is 23.629. Remember, this is degrees. And how do I get from degrees to radians? Well, I just remember, here's my circle. If this is my circle, then the whole thing around is 2 pi. It's also 360 degrees. Or I just remember halfway around is pi, and it's 180 degrees. So I have this nice relationship that to go 180 degrees, it's also half a pi, which is just pi. So when I see degrees here, I know it's pi over 180 degrees. And then I would end up with it in radians. So there's our shear strain. It also says, what is shear stress? What is shear stress? Well, the stress part is going to be going over the front of this block where the metal U is attached to it. So if I could look at in here, so on this side, I wonder if I can get a different color that'll show up. If I were able to look at where they were attached, that would be the connection. Can you kind of see that? Not really. It would be the connection of the front of this rubber block. So we're looking at the height of the rubber block and then the width into the paper. The height of the rubber block and the width. Where would we glue? We would glue it in this connection point. So that area has to be 22 times 25. It's that front part of that block. Okay? So I know that shear stress is V over A. So I have to calculate V and A. Okay? So free body diagram, if I'm pushing down with 690 newtons, it told us we were pushing down, then if it's symmetric, it's evenly distributed. So on the upper U, if I'm pushing down 690, then on each side we have a resisting shear force of 345 newtons. Okay, now that I've got glue in here, so here's the glue that's going to bond that frame to the rubber block. This shear is now pushing down, remember equal and opposite on the frame, on the block, equal and opposite, equal and opposite. When I put it back together like this, I don't see the internal, okay? So my shear has to be that 345 newtons, and that cross-sectional area is, it is that 22 millimeters tall, okay, and it's 25 millimeters back into the page. Okay, it goes back into the page like so, and it's acting on that. So it is 22 by 25 is that shear force area. And I can see that these are in millimeters, so I need to divide both of them by 1,000 to get them into meters. And I'm going to get then my shear stress is a very large number, but we can cut off 3 of the zeros and call it 627 kilopascals shear stress. So you have to remember what is the difference. What is shear strain? What is shear stress? Strain is the deformation. Stress is that force over area.